Hi guys, I'm back again. Today we're going to talk about Hess's Law and being able to calculate how much heat a certain reaction will produce or how much heat it will take for a certain reaction to produce. Hess's Law is a very, very powerful equation, and it's also fairly simplistic. It looks very, very complex, but when you boil it down, it's essentially the delta H, or the change in heat of a reaction, or this is actually really stands for enthalpy. It's slightly different than heat, but for all intents and purposes, they're the same thing. So the change in enthalpy of a reaction equals the summation, or the sums, or adding up the delta H's of the component reactions. So these are the component reactions. These are how we get to this thing. It's not really a reaction mechanism because it doesn't follow a set of linear steps, but this is how all of my reactants and products are formed. So we take this and we figure out how all my reactants and products are formed, and then we're able to see the energies, and by comparing the energies in my reactants versus products, we can see how much will be released, or that change. This is essentially going back to the potential energy diagram, you know, where it looks kind of like that. So I'm essentially going to calculate all of the energy that's in my reactants. I'll calculate all the energy that's in my products, and I'll be able to measure that difference. And that difference will be my delta H. Okay, so here's how I'm going to do it. I've written the overall balanced reaction, C2H4 plus H2 yields C2H6. And then I've written down the component reactions, we'll call them. They're not really reaction mechanisms, so we'll call them the component reactions. These are given, as are their delta H values. Also, just to make things pop and look a little easier, I've taken the components that we're looking for, these three compounds in my balanced equation, and I've just written them in red. And they turn out to be the first ones in every reaction series. They're not always the first ones. They could be a product, they could be a reactant, they could be wherever. But for simplicity's sake, I wrote them in red so they kind of pop a little bit. And I've also put them at the beginning. I put them first. Okay, so the first thing we do is we just take this step by step. There's a lot going on here. It looks very complex, but the principle's fairly simple. We want to rearrange, manipulate, change these reactions so that everything crosses out except for the red compounds. So we can multiply by coefficients, we can flip our reactions. The only rule is whatever we do to the reaction, we have to do to our delta H value as well. And as long as we do that, everything should work out perfectly. Okay, so we'll start with our first reaction. Why not? I have C2H4 as a reactant, and here I have C2H4 as a reactant. So that's perfect. I have one here, one here. I don't need to change anything. It's exactly where it needs to be. So I'm not going to change anything on my reaction. I'm not going to change my delta H value at all. All right, going down to our second one. I have C2H6 here as a reactant. Up in my balanced reaction, though, I have it as a product. What that means is I'm going to have to flip-flop or flip this reaction. So I'm going to have to take this and flip this entire reaction. What that means is I'm going to have to flip my delta H value as well, so let me do that first. So it's negative, I'm going to flip it and make it positive. Okay. And give me a second, I'm going to rewrite the second equation, and I'm just going to flip it. I'm just going to write it backwards. Okay. I'm not going to really change anything else about it. I'm not multiplying it by any coefficients. So I have 3 H2O, and those are liquid, plus 2 CO2s, those are gaseous. 7/2 O2, gaseous, plus, and I'm going to do this next one in red, so we can still kind of see exactly what's going on. C2H6, gaseous. Okay, perfect. So I've got this on this side. I've got it on the product side with the product. I have the same correct numbers. I have one here and one here. So that's great. All right, so we're going to move down to our third reaction. In my third reaction, I have H2 gas here as a reactant. I have H2 gas here as a reactant. I have one here, one here. Perfect. I don't need to change this at all. And then I have, obviously, these other things. So I'm not going to change this. I'm not going to change my delta H value. what I'm going to do right now is I'm just going to add up my reactions. So I'm going to treat this almost like it's an equation. And in this case, I'm just going to use black. But I'm going to just kind of add up all of my reactants, add up all of my products, and just see what my overall reaction is. I'm not going to cancel anything out yet. So I have C2H4, gaseous, plus I have, let me cross these out as I'm doing it, I have 6 halves O2 here, and 1 half O2 here, so that's 7 halves O2 total. Cross those out. Plus 3 H2Os. Those are liquids. Plus 2 CO2s. Those are gaseous. Plus an H2. Okay, so these are all of my reactants, and I'm going to run out of room. So now you would just continue this reaction here, but I only have till right about here-ish until the camera kicks off. So I'm going to write my products underneath. It's not really the best way to do it, but given our limitations, it's what we're going to do. Okay, so I have 2 CO2s, plus 2 H2s here and 1 down here, so 3 H2Os. Plus, let me get rid of that, 7 O2s, sorry, 7 halves O2s, plus my C2H6. Okay, let me put the state of matter. Okay, so I have my reactants here. I'm going to label these because it's a little bit of a weird way to write it. I have my reactants on top, my products on the bottom. And now I'm just going to start canceling out the things that are the same. So I take a look. I have 2 CO2 gases here as a reactant, and I have 2 CO2 gases as a product. All right? So if we think about it in terms of, let's say, a math equation, if they're on both sides of the equal sign, in this case it's an arrow, they would cancel out. So I'm just going to cancel them out. It's just math. There we go. I have 7 halves O2 as a reactant, and I have 7 halves O2 as a product. Erase those guys. Okay. And then I have 3 H2Os as a reactant and 3 H2Os as a product. And this is all I'm left with. C2H4 plus H2 yields C2H6. Okay. Let me rewrite this. Let me kind of condense this down a little bit. Notice that matches my balanced reaction in the beginning. So that's fine. Just like I summated, I don't know if that's a real word, just like I summed my reactions, I need to sum my delta H's. Okay. So I will grab a calculator for this because my mental math abilities are not crazy. So negative 1,411. These are all, the unit for these are all kilojoules per mole. All right, these are all kilojoules per mole. I didn't write that because I was worried about space. So negative 1,411 plus 1,560 minus 285.8. And I get, for the delta H of this entire reaction is negative 136.8 kilojoules per mole. Couple of things to note. This is an exothermic reaction, meaning that this reaction will produce enthalpy, or this reaction will produce heat. It's not highly exothermic, but it is an exothermic reaction. Okay, so this is how we solve a Hess's Law problem. Hopefully you're able to follow along. There is one other type of Hess's Law. It's called the delta H of formation that we will cover in the next video. All right, thank you very much, and good luck.